Tonight we're going to talk about the one speed limit that controls everything in the universe. The speed of light. You've heard this number before, 186,000 miles per second. It sounds fast, and it is. But here's what most people don't realize. This isn't just a speed. It's a cosmic law that breaks our understanding of reality itself. Nothing can go faster than light. Not spaceships, not particles, not information, not even gravity. And when you really dig into why this limit exists and what it means, you discover something deeply unsettling. The universe doesn't work the way you think it does. Time isn't constant. Distance isn't fixed. And the faster you move, the more reality itself warps around you. By the end of tonight, you're going to understand why the speed of light isn't just about how fast photons travel. It's about the fundamental structure of space and time, and why breaking this limit isn't just difficult, it's impossible by the laws of physics. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what light actually is. For most of human history, nobody knew. People could see light. They could feel warmth from the sun. They understood that light let you see things in the dark. But what light actually was remained mysterious. The ancient Greeks debated whether light came from our eyes reaching out to touch objects, or whether objects sent something to our eyes. They got it wrong on the details, but they were asking the right questions. By the 1600s, scientists were having serious debates about light's nature. Isaac Newton thought light was made of tiny particles, little corpuscles that traveled in straight lines. This explained some things well, like why light casts sharp shadows and why it reflects off mirrors at predictable angles. Other scientists like Christian Huygens thought light was a wave, like ripples spreading across a pond. This explained different phenomena, like how light bends when it passes through glass or water. Both camps had evidence. Both had good arguments, and neither could conclusively prove the other wrong with the technology available at the time. The debate would continue for over 2 centuries. In the 1860s, a Scottish physicist named James Clerk Maxwell solved a completely different problem that unexpectedly answered the question of what light is. Maxwell was studying electricity and magnetism. These two forces had been known for centuries, but nobody understood how they were connected. Maxwell worked out the mathematics describing electric and magnetic fields, and when he put all his equations together, something remarkable emerged. The equations predicted that changing electric fields would create magnetic fields, and changing magnetic fields would create electric fields. And if you had both happening together, they would create a self-sustaining wave, an electromagnetic wave that would travel through space without needing any medium to carry it. When Maxwell calculated how fast these electromagnetic waves would travel, he got a specific number from his equations, about 186,000 miles per second. He realized immediately what this meant. Light was an electromagnetic wave. Visible light, the light you see with your eyes, is just one type of electromagnetic radiation. There's a whole spectrum. Radio waves are electromagnetic radiation with long wavelengths, measured in meters or even kilometers. Microwaves have shorter wavelengths, measured in centimeters. Infrared radiation is shorter still, measured in micrometers. Then comes visible light, the narrow band of electromagnetic radiation that human eyes can detect, with wavelengths measured in hundreds of nanometers. Beyond visible light, there's ultraviolet radiation, X-rays, and gamma rays, each with progressively shorter wavelengths and higher energy. All of these are the same fundamental phenomenon, electromagnetic waves, just with different wavelengths and frequencies, and all of them travel at the same speed in a vacuum, the speed of light. But here's the first strange thing. about the speed of light. It's always the same speed, no matter how you measure it. This sounds obvious until you think about it carefully. Imagine you're standing still and you measure the speed of a car driving past you at 60 miles per hour. Now imagine you're in another car, also driving at 40 miles per hour in the same direction. You measure that first car's speed again, and now it appears to be going only 20 miles per hour relative to you because you're moving too. If you're driving toward that car head-on at 40 miles per hour, it appears to be approaching you at 100 miles per hour. The car's speed relative to you depends on your motion. That's how speeds work for everything in everyday experience. Velocities add and subtract. But light doesn't work this way. If you're standing still and you measure light traveling past you, you get 186,000 miles per second. If you're traveling at half the speed of light in the same direction as the light beam and you measure its speed again, you still get 186,000 miles per second, not 93,000 miles per second like you'd expect. The full 186,000 miles per second. This makes no sense, according to everyday experience, but it's been confirmed by countless experiments. The speed of light is constant, always, everywhere. For every observer, regardless of how fast they're moving or in what direction. This fact, this one weird property of light, is what forced Albert Einstein to completely reimagine how the universe works. Einstein was 26 years old in 1905, working as a patent clerk in Bern, Switzerland. He wasn't a professor, didn't have access to university resources, and was doing physics in his spare time. That year, he published a paper called On the Electrodynamics of Moving Bodies. Today, we call the ideas in that paper special relativity. Einstein started with two principles. First, the laws of physics are the same for all observers moving at constant velocity. This principle is called Galilean relativity, and it had been accepted since the 1600s. If you're in a car moving smoothly at constant speed with the windows blocked, you can't tell whether you're moving or standing still by doing any physics experiment inside the car. Everything behaves the same. Second, the speed of light is constant for all observers, regardless of their motion. This was the new and radical part. These two principles seem incompatible. If light travels at 186,000 miles per second for a stationary observer, and also at 186,000 miles per second for an observer moving at half the speed of light, how is that possible? Einstein's answer was revolutionary. Time and space are not absolute. They adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of a stationary observer. And distances in the direction you're moving contract, they actually get shorter. This is called time dilation and length contraction, and it's not an illusion or a trick. It's what actually happens to time and space. Let me give you a concrete example. Imagine you have a twin. You get on a spaceship and accelerate to 87% of the speed of light, about 162,000 miles per second. You travel to a star 10 light-years away and come back. From Earth's perspective, the trip takes just over 23 years because you traveled 20 light-years total at 87% light speed. Your twin, who stayed on Earth, ages 23 years, but you, traveling at that speed, only age about 11.5 years. You come back younger than your twin. This isn't science fiction. It's real physics, confirmed by experiments with atomic clocks on airplanes and satellites. The faster you move, the slower time passes for you relative to stationary observers. At everyday speeds, this effect is tiny, far too small to notice. If you drive across the country at highway speeds, you age a few nanoseconds less than if you'd stayed home. But as you approach the speed of light, the effect becomes dramatic. At 90% of light speed, time runs at about 44% of normal. At 99% of light speed, time runs at about 14%. At 99.9% of light speed, time runs at about 4.5%. The closer you get to light speed, the more extreme the time dilation becomes. At exactly the speed of light, time would stop completely from the perspective of stationary observers. From a photon's perspective, if a photon could have a perspective, no time passes at all during its journey. A photon emitted from a distant star, billions of light years away, experiences its entire journey instantaneously from its own frame of reference. It's emitted and absorbed in the same moment as far as the photon is concerned. Now here's where things get really strange. Why can't you accelerate to the speed of light? It's not just that it's difficult or that we don't have powerful enough engines. It's fundamentally impossible according to the laws of physics. Here's why. As you accelerate and your speed increases, your mass effectively increases from the perspective of stationary observers. This isn't mass being added, it's what's called relativistic mass, a consequence of how energy and mass are related at high speeds. The faster you go, the more massive you become, and the more energy is required to accelerate you further. At everyday speeds, this effect is negligible, but as you approach light speed, your effective mass increases dramatically. At 90% of light speed, your effective mass is about 2.3 times your rest mass. At 99% of light speed, your effective mass is about 7 times your rest mass. At 99.9% of light speed, your effective mass is about 22 times your rest mass. As you get closer and closer to light speed, your effective mass approaches infinity. To actually reach light speed would require infinite mass, which would require infinite energy to accelerate. You can't get infinite energy, so you can't reach light speed. This applies to anything with mass. Spaceships, particles, people, planets, anything with any mass at all cannot reach the speed of light. You can get very close. You can reach 99.9999% of light speed if you have enough energy. But you can never reach 100%. There's always a gap, and closing that gap requires more and more energy without limit. Only things with zero mass can travel at light speed. Photons have zero mass, so they travel at light speed. Gravitons, the hypothetical particles that carry the gravitational force, would have zero mass, so they would also travel at light speed. Anything with zero mass must travel at light speed, and anything with any mass at all cannot. This is a fundamental law of the universe, as absolute as any law gets in physics. So the speed of light is not just the fastest speed possible, it's a barrier that divides the universe into two categories. Things with zero mass that travel at light speed, and things with any mass that can never reach light speed. There's no middle ground. Let's talk about what this means for space travel. The distances between stars are enormous, measured in light years. The distance light travels in 1 year. The nearest star system to our Sun is Alpha Centauri, about 4.37 light-years away. At light speed, it would take 4.37 years to get there. But we can't travel at light speed. With current rocket technology, the fastest spacecraft humans have built is the Parker Solar Probe, which reached about 430,000 miles per hour relative to the Sun. That sounds fast, but it's only about 0.064% of the speed of light. At that speed, reaching Alpha Centauri would take about 6,800 years. That's not a journey humans can make with current technology. Even if we could build a spacecraft that reached 10% of light speed, which would require technology far beyond anything we currently have, the trip to Alpha Centauri would still take 43.7 years. You'd need either a multi-generational ship where the people who arrive are descendants of those who left, or some form of suspended animation, or propulsion systems we haven't invented yet. And that's just to reach our nearest stellar neighbor. Most interesting destinations are much farther away. The center of our galaxy is about 26,000 light-years away. The Andromeda Galaxy is about 2.5 million light-years away. The observable universe extends about 46.5 billion light-years in every direction, even traveling at light speed, which is impossible for anything with mass. You couldn't explore even a tiny fraction of the universe in a human lifetime. The speed of light doesn't just limit how fast we can travel, it limits how much of the universe is accessible to us. There are regions of space so far away that light from them will never reach us because the space between us and them is expanding faster than light can cross it. This is possible because space itself can expand faster than light. The speed limit applies to objects moving through space, but not to space itself. The universe's expansion means there's a cosmic horizon, a boundary beyond which we can never see or reach, no matter how long we wait or how advanced our technology becomes. Those regions are forever beyond our reach, not because we lack the technology to get there, but because the laws of physics make it impossible. Now, let's talk about information and causality. Nothing can travel faster than light. That includes information. You cannot send a message or a signal or any kind of information faster than light. This has profound implications for how the universe works. Imagine something happens right now on a planet orbiting Alpha Centauri. Maybe a civilization decides to send us a message. That message, traveling at light speed, takes 4.37 years to reach us. We receive it 4.37 years after it was sent. If we immediately send a reply, that reply takes another 4.37 years to get back to them. The round-trip communication time is 8.74 years. For more distant locations, this gets worse. A civilization 1,000 light-years away would have a round-trip communication time of 2,000 years. You could send a message, and neither you nor your children nor your grandchildren would live to see the reply. Only your distant descendants might hear back. This creates a fundamental isolation in the universe. Distant parts of the universe cannot communicate with each other in any meaningful real-time way. The speed of light creates a cosmic speed limit on information, and this limit means that cause and effect are constrained. An event that happens here and now cannot affect a distant location until enough time has passed for light to travel there. Your actions right now cannot influence Alpha Centauri for at least 4.37 years. They cannot influence a galaxy 1,000,000 light-years away for at least 1,000,000 years. This is what physicists mean when they talk about causality. Cause must precede effect, and the speed of light determines how quickly effects can propagate. This has been tested extensively in quantum mechanics. Particles can be entangled, meaning their properties are correlated in ways that seem to allow instantaneous influence. If you measure one entangled particle and its spin up, the other particle immediately becomes spin down, even if it's on the other side of the galaxy. This seems to violate the speed of light limit, but it doesn't. You can't use entanglement to send information faster than light. The correlations are real, but they can't be used for communication. The details are subtle and require quantum mechanics to fully explain, but the bottom line is this: no information travels faster than light, even in quantum mechanics. The speed of light limit holds, always. Let's talk about what happens when you try to approach light speed. Beyond time dilation and mass increase, there are other strange effects. One is called the relativistic Doppler effect. You're probably familiar with the regular Doppler effect for sound. When an ambulance approaches you, its siren sounds higher pitched because the sound waves are compressed. When it moves away, the siren sounds lower pitched because the waves are stretched. Light does the same thing, but with a twist because of time dilation. If you're traveling very fast toward a light source, the light appears blue-shifted, meaning its wavelength gets shorter and it looks bluer. If you're traveling away from a light source, it appears redshifted, meaning its wavelength gets longer and it looks redder. At extreme speeds approaching light speed, this effect becomes dramatic. Stars in front of you would appear intensely blue or even shift into ultraviolet and X-ray frequencies. Stars behind you would appear red or shift into infrared and radio frequencies. Eventually, at speeds very close to light speed, most of the visible light would shift out of the visible spectrum entirely. There's also an effect called relativistic beaming. As you approach light speed, light from stars in front of you gets concentrated into a smaller and smaller cone directly ahead. Stars off to the sides become dimmer or disappear entirely from your view. Most of the light in the universe would appear to come from a small bright spot directly in front of your spacecraft. The view from a ship traveling at 99.9% of light speed would be bizarre. A small, intensely bright, highly blue-shifted spot ahead, darkness to the sides, and a dim red-shifted glow behind. Nothing like the serene star field depicted in most science fiction. Another consequence of traveling near light speed is radiation. Space isn't empty. There are atoms and particles scattered throughout space, mostly hydrogen, at very low density. In normal circumstances, this interstellar medium is harmless, but if you're traveling at a significant fraction of light speed, these particles hit you with enormous energy. At 90% of light speed, every hydrogen atom you encounter hits with the energy of a particle accelerated in a major physics laboratory. At 99.9% of light speed, the impacts are even more energetic. The hull of your spacecraft would be bombarded by what amounts to a continuous stream of radiation and high-energy particles. This would heat the hull, damage electronics, and pose serious dangers to any crew. You'd need substantial shielding, which adds mass, which requires more energy to accelerate, creating an engineering challenge on top of the already enormous challenge of reaching such speeds. The cosmic microwave background radiation, the leftover glow from the Big Bang that's present everywhere in the universe, would also become a problem. At rest, this radiation is very cold, only about 2.7 degrees above absolute zero, but at extreme speeds, it would be blue-shifted into higher energies. At high enough speeds, it would appear as intense gamma radiation, deadly to any living thing. This is sometimes called the cosmic microwave background wall, a theoretical barrier to ultra-high-speed travel created by the universe's own background, radiation becoming dangerous. So even if you could somehow reach very high speeds, the environment itself becomes hostile. Now, let's talk about practical attempts to approach these speeds. The fastest spacecraft humans have ever built, the Parker Solar Probe, achieves its speed by falling toward the Sun and using multiple gravitational assists from Venus. This isn't sustainable for interstellar travel. You need propulsion that works in deep space, far from any gravitational assists. Chemical rockets, the kind we use for most space travel today, are limited by the energy density of chemical reactions. The most efficient chemical rocket fuels can reach exhaust velocities of about 2.8 miles per second. To accelerate a spacecraft to a significant fraction of light speed using chemical rockets would require absurd amounts of fuel. The rocket equation, formulated by Konstantin Tsiolkovsky, describes this problem. The mass ratio, the ratio of initial mass with fuel to final mass without fuel, grows exponentially with the desired change in velocity. To reach even 1% of light speed with chemical rockets would require a mass ratio so large that the fuel tanks would be larger than planets. It's not practical. Nuclear propulsion offers better performance. Nuclear thermal rockets, which heat propellant using a nuclear reactor, can achieve exhaust velocities of about 5 to 6 miles per second, better than chemical rockets, but still far from what's needed. Nuclear pulse propulsion. The concept behind Project Orion from the 1950s and 60s involves detonating nuclear bombs behind a spacecraft and riding the shockwave. This could theoretically achieve exhaust velocities of about 62 miles per second, maybe higher with advanced designs. Even then, reaching 10% of light speed would require a massive spacecraft with a huge supply of nuclear bombs. Project Orion was never built, partly because of the Partial Test Ban Treaty, which prohibits nuclear explosions in space. Ion drives and other electric propulsion systems can achieve very high exhaust velocities, up to about 124 miles per second for some designs. The problem is, they produce very little thrust. They can run for months or years, gradually accumulating speed, but accelerating to relativistic speeds would take enormous amounts of time and energy. The most promising concept for reaching a significant fraction of light speed is some form of matter-antimatter propulsion. When matter and antimatter meet, they annihilate, converting their entire mass into energy with 100% efficiency. According to Einstein's famous equation, E equals mc squared. This is the most energetic reaction possible in physics. A matter-antimatter rocket could theoretically achieve exhaust velocities approaching the speed of light itself. The problem is, we can't produce or store antimatter in meaningful quantities. Creating antimatter requires enormous amounts of energy. Current estimates are about $10 billion per milligram, and storing it without it touching normal matter and annihilating is extraordinarily difficult. We've only ever created tiny amounts of antimatter, measured in nanograms, and only stored it for minutes or hours. Building a matter-antimatter rocket with enough fuel to reach relativistic speeds is far beyond current technology. It might be possible in principle, but we're nowhere close to achieving it. There are more speculative ideas. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, would scoop up hydrogen from interstellar space and use it as fuel in a fusion reactor. This would solve the fuel problem, since you'd collect fuel as you go. The challenge is that interstellar space has very low density, only about 1 hydrogen atom per cubic centimeter on average. You'd need a magnetic scoop hundreds or thousands of miles wide to collect enough fuel. And fusion is difficult. We haven't achieved sustained fusion for power generation on Earth yet, much less in a spacecraft traveling through space. Another idea is the light sail. Instead of carrying fuel, you use a large reflective sail pushed by light pressure. Sunlight exerts pressure, a very small force, but over time it can accelerate a lightweight sail to significant speeds. The Breakthrough Starshot project proposes using powerful lasers on Earth to push tiny spacecraft, weighing only grams, to 20% of light speed. The idea is to send thousands of these tiny probes to nearby star systems. They'd reach Alpha Centauri in about 20 years. This concept faces enormous engineering challenges. The laser array would need to be extremely powerful. The sails would need to be incredibly light and reflective. The probes would need to survive being accelerated to 20% of light speed in a matter of minutes, and there's no way to slow down once they get there. They just fly past their target at tremendous speed with only minutes to collect data. But it's based on real physics and might be achievable within the next few decades if we commit resources to it. Even then, 20% of light speed is impressive by current standards, but it's still far from the speed of light itself. Reaching 90% or 99% of light speed remains firmly in the realm of theoretical physics and far future technology. Now, let's address a question people often ask. What about warp drives or wormholes? These ideas come up a lot in science fiction, and they're based on real physics, sort of, but they're not practical ways to exceed the speed of light. A warp drive, as described in physics papers, would work by contracting space in front of a spacecraft and expanding space behind it. The spacecraft would remain stationary in its local region of space, but that region would move faster than light relative to distant points. This doesn't violate relativity, because the spacecraft isn't moving through space faster than light. Space itself is moving. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is the most famous warp drive concept. The problem is, it requires exotic matter with negative mass or negative energy density. We've never observed anything with negative mass. There are some quantum effects that can produce negative energy density in very specific circumstances, like the Casimir effect, but nowhere near the amounts needed for a warp drive. Current estimates suggest you'd need the negative mass equivalent of several Jupiter masses to create a warp bubble large enough for a spacecraft. Even if exotic matter exists or can be created, we have no idea how to accumulate it in the quantities needed or how to manipulate it to create a warp bubble. The Alcubierre drive is mathematically consistent with general relativity, but that doesn't mean it's practical or even possible. Wormholes, shortcuts through space-time connecting distant regions, are also consistent with general relativity in principle, but they have the same problem. They require exotic matter to keep them open and stable. A wormhole without exotic matter would collapse instantly, pinching off before anything could travel through it. And even if you could create and stabilize a wormhole, you'd need to get one end of it to your destination, which means traveling there at sublight speed first. Wormholes don't help you reach new destinations faster. They only help you travel between destinations you've already reached. Plus, there are potential causality problems. Some wormhole configurations could allow time travel, creating grandfather paradoxes and other logical contradictions. Many physicists think the laws of physics might prohibit such configurations, but we don't fully understand the constraints. So while warp drives and wormholes are fun to think about, and they're not ruled out by known physics, they're extremely speculative and require technologies and materials we have no idea how to create. They're not practical solutions to the speed of light limit, at least not with anything resembling current understanding. Let's talk about what we've actually observed traveling at or near light speed. Particles in cosmic rays, high-energy particles from space, routinely travel at 99.9% of light speed or higher. The highest energy cosmic rays ever detected have energies around 10 to the power of 20 electron volts. These are particles, probably protons, traveling incredibly close to the speed of light. Where do these particles get such enormous energies? We don't know for certain. Possible sources include supernova remnants, active galactic nuclei, or gamma-ray bursts. Whatever the source, these natural particle accelerators are far more powerful than anything we can build. The Large Hadron Collider, the most powerful particle accelerator on Earth, accelerates protons to about 99.999991% of light speed. That's fast enough to make a proton circle the 17-mile tunnel about 11,000 times per second. At those speeds, time dilation is significant. From the proton's perspective, it circles the ring much faster because distances are contracted. From our perspective, the proton lives much longer before decaying because time runs slower for it. We use particle accelerators to study high-energy physics, to create conditions similar to those moments after the Big Bang, and to discover new particles. The Higgs boson, discovered in 2012, was created by colliding protons at near light speed. The collision had enough energy to convert into mass, creating particles that don't normally exist. This is another consequence of Einstein's E equals mc squared. Energy can be converted into mass, and at high enough energies, you can create massive particles out of pure energy. Every time we accelerate particles to near light speed and collide them, we're testing relativity. And every single time, the results match Einstein's predictions. Time dilation, length contraction, mass-energy equivalence, all of it has been confirmed thousands of times. Special relativity isn't speculation, it's one of the most thoroughly tested theories in all of physics. Let's dive deeper into some specific examples of how the speed of light shapes our understanding of the universe. Start with the Sun. The Sun is about 93 million miles from Earth on average. Light from the Sun takes about 8 minutes and 20 seconds to reach us. This means when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes and 20 seconds ago. If the Sun suddenly vanished, winked out of existence, we wouldn't know for 8 minutes and 20 seconds. For those 8 minutes, we'd still see the Sun in the sky. We'd still feel its warmth. The Earth would continue orbiting where the Sun used to be. Only after 8 minutes and 20 seconds would the light stop, darkness would fall, and Earth would fly off in a straight line, no longer held in orbit by the Sun's gravity. This seems strange, but it's a direct consequence of information traveling at finite speed. The information that the Sun has disappeared cannot reach Earth faster than light travels. Mercury, the closest planet to the Sun, is about 36 million miles from the Sun on average. Light takes about 3 minutes and 13 seconds to travel from the Sun to Mercury. Venus is about 67 million miles from the Sun. Light takes about 6 minutes. Mars is about 142 million miles from the Sun. Light takes about 12 minutes and 40 seconds. Jupiter, the largest planet, is about 484 million miles from the Sun on average. Light takes about 43 minutes to reach Jupiter from the Sun. Saturn is about 886 million miles from the Sun. Light takes about 1 hour and 19 minutes. Uranus is about 1.8 billion miles from the Sun. Light takes about 2 hours and 40 minutes. Neptune, the farthest planet, is about 2.8 billion miles from the Sun. Light takes about 4 hours and 10 minutes to reach Neptune. This means when we observe these planets through telescopes, we're seeing them as they were hours ago. When the Voyager 2 spacecraft flew past Neptune in 1989, commands sent from Earth took over 4 hours to reach the spacecraft, and signals from the spacecraft telling us what it was seeing took another 4 hours to return. Total communication round-trip time was over 8 hours. Mission controllers had to plan every maneuver carefully and send commands well in advance because they couldn't react in real time to what the spacecraft was doing. By the time they saw a problem, it would be over 4 hours old, and by the time their corrective commands reached the spacecraft, over 8 hours would have passed. The spacecraft had to be largely autonomous, capable of executing complex maneuvers on its own. Beyond Neptune lies the Kuiper Belt, a region of icy bodies including Pluto. Pluto is about 3.7 billion miles from the Sun on average. Light takes about 5.5 hours to reach Pluto. When the New Horizons spacecraft flew past Pluto in 2015, it was over 4.5 light hours from Earth. Every command took over 4.5 hours to arrive. Every image took over 4.5 hours to return. The spacecraft was on its own during the critical flyby hours. Everything had to be pre-programmed months in advance. Now let's step outside the solar system entirely and look at nearby stars. Proxima Centauri, the nearest star to our Sun, is about 4.24 light-years away. That's about 25 trillion miles. Light takes 4.24 years to travel from Proxima Centauri to Earth. Alpha Centauri A and B, the two bright stars in the Alpha Centauri system, are about 4.37 light-years away. Barnard's star is about 5.96 light-years away. Sirius, the brightest star in the night sky, is about 8.6 light-years away. All of these stars are our nearest neighbors in the galaxy, and all of them are multiple light-years away. When we look at Sirius tonight, we're seeing light that left that star 8.6 years ago. If there were a planet orbiting Sirius with intelligent life, and they were looking at our Sun right now, They'd be seeing the sun as it was 8.6 years ago. They'd be seeing Earth as it was 8.6 years ago. If humans sent a signal towards Sirius today, it would take 8.6 years to arrive, and any response would take another 8.6 years to return. Total round-trip communication time would be 17.2 years. That's a generation. Our galaxy, the Milky Way, is about 100,000 light-years in diameter. Light takes 100,000 years to cross from one side to the other. The Sun is about 26,000 light-years from the galactic center. When we observe the center of our galaxy, we're seeing it as it was 26,000 years ago. Back when humans were still hunter-gatherers, before agriculture, before cities, before writing. The supermassive black hole at the center of our galaxy, Sagittarius A star, is 26,000 light-years away. We've observed stars orbiting this black hole, stars that complete their orbits in years or decades. But we're watching these orbits in extreme slow motion from our perspective because of the light travel time. When we see a star complete one orbit around the black hole, we're watching something that actually happened 26,000 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. Light takes 2.5 million years to travel from Andromeda to Earth. When you look at Andromeda through a telescope, you're seeing it as it was 2.5 million years ago, before modern humans existed, before the genus Homo appeared. Our distant ancestors 2.5 million years ago were early hominids just beginning to use stone tools. The Andromeda you see tonight is from that era. The actual current state of Andromeda is unknowable to us. We cannot see it as it is now. We can only see it as it was in the distant past. The universe itself is about 13.8 billion years old. The most distant galaxies we've observed are about 13.4 billion light-years away in what's called comoving distance, accounting for the expansion of the universe. The light we see from these galaxies was emitted when the universe was only about 400 million years old. These are some of the first galaxies to form after the Big Bang. Small, irregular, filled with hot young stars. Very different from modern galaxies like the Milky Way. When we observe these ancient galaxies, we're literally looking back to near the beginning of cosmic time. We're seeing the universe in its infancy. This is only possible because light takes time to travel and because the universe is vast. The cosmic microwave background, the afterglow of the Big Bang, comes from about 13.8 billion light-years away. This is light that was emitted when the universe was only about 380,000 years old. Before that, the universe was opaque, filled with hot plasma that scattered light. But when the universe cooled enough for atoms to form, light could travel freely for the first time. That light has been traveling through space ever since, stretched and redshifted by the universe's expansion until it reaches our telescopes, today as microwave radiation. When we map the cosmic microwave background, we're seeing the oldest light in the universe. We're seeing the universe as it was just a few 100,000 years after the Big Bang. This is as far back as we can see with light. The point is, the speed of light creates this cosmic archaeological record. Every time we look farther into space, we look farther back in time. The universe presents itself to us as a history book written in light. Near stars show us the recent past. Distant galaxies show us the distant past. And the cosmic microwave background shows us the very early universe. All because light has a finite speed, and the universe is vast enough that light takes billions of years to cross cosmic distances. Let me talk about attempts to measure the speed of light throughout history. For most of human history, people assumed light traveled instantaneously. You open your eyes and you see, there seemed to be no delay. Galileo Galilei tried to measure the speed of light in the early 1600s. He and an assistant stood on hilltops a few miles apart at night with lanterns. Galileo would uncover his lantern, and when his assistant saw the light, the assistant would uncover his lantern. Galileo would measure the time delay. The problem is, the speed of light is so fast that the delay over a few miles is tiny, far too short to measure with 1600s technology. Galileo concluded only that light was either instantaneous or extremely fast. The first successful measurement came from Ole Rømer, a Danish astronomer, in 1676. Rømer was observing Jupiter's moon Io, which orbits Jupiter every 42.5 hours or so. Io regularly passes behind Jupiter in eclipses that can be timed precisely. Rømer noticed that the eclipses occurred later than predicted when Earth was farther from Jupiter and earlier than predicted when Earth was closer. The difference was about 22 minutes over the course of a year, as Earth's distance from Jupiter varied. Rømer correctly realized this was because light took time to travel the extra distance when Earth and Jupiter were on opposite sides of the Sun versus the same side. The diameter of Earth's orbit is about 186 million miles. Light taking 22 minutes to cross this distance gives a speed of about 140,000 miles per second. Not quite right. Rømer's value was too low, but it was in the right ballpark, and it proved that light has a finite speed. Over the next 2 centuries, measurements improved. James Bradley in 1728 measured the aberration of starlight and calculated a speed of about 185,000 miles per second, much closer to the true value. Albert Michelson spent decades refining these measurements. In 1879, he got 186,355 miles per second. By 1926, he had improved it to 186,285 miles per second. His final measurements in the 1930s gave values very close to the modern accepted value. Today, we define the speed of light to be exactly 299,792,458 meters per second. This is 186,282.397 miles per second. We don't measure it anymore, we define it. And we define the meter in terms of how far light travels in a certain fraction of a second. This makes the speed of light a fundamental constant that defines our system of units. Let's talk about gravitational waves, another phenomenon related to the speed of light. When massive objects like black holes or neutron stars orbit each other, they create ripples in space-time. These ripples propagate outward at the speed of light. Not faster, not slower, exactly light speed. This was predicted by general relativity and confirmed by the detection of gravitational waves in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO detected gravitational waves from 2 black holes, each about 30 times the Sun's mass, orbiting each other and merging about 1.3 billion light-years away. The waves traveled for 1.3 billion years across space, arrived at Earth, and were detected by LIGO's incredibly sensitive instruments. The fact that gravitational waves travel at light speed is significant. It means gravity is not instantaneous. When 2 masses orbit each other, the gravitational force between them is not directed at where the other mass is now, but at where it was 1 light travel time ago. For the Earth and the Sun, this is 8 minutes and 20 seconds. The Sun's gravity that Earth feels right now is pointing to where the Sun was 8 minutes and 20 seconds ago. Fortunately, the Sun is moving slowly relative to Earth, so the difference between where it was 8 minutes ago and where it is now is tiny. The error is negligible for planetary orbits, but in principle, gravity propagates at finite speed, the speed of light, just like electromagnetic radiation. This is a feature of general relativity and has been confirmed by observations. If gravity propagated instantaneously, we'd see violations of causality and other problems. The finite speed of gravity is necessary for the consistency of physics. Now let's return to cosmology and think about the expansion of the universe. The universe is expanding, and distant galaxies are receding from us. Edwin Hubble discovered this in the 1920s by observing that galaxies farther away have larger redshifts. The redshift is a stretching of light waves as space expands while the light travels. The farther a galaxy is, the more space has expanded while its light traveled to us, and the greater the redshift. Hubble's law states that the recession velocity of a galaxy is proportional to its distance. Galaxies twice as far away are receding twice as fast. At some distance, the recession velocity exceeds the speed of light. This happens at about 14 billion light-years or so. Galaxies beyond this distance are receding faster than light. Their recession velocity, measured as the rate at which the distance increases, is greater than 186,000 miles per second. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying the galaxies with it. General relativity allows space to expand at any rate, even faster than light. The speed limit applies to objects moving through space, not to space itself. However, light emitted right now from a galaxy that's currently receding faster than light will never reach us. The space between us and the light is expanding faster than the light can make progress toward us. The light is like a person on a treadmill running forward, while the treadmill accelerates backward faster than they can run. They're making no progress toward the front of the treadmill, even though they're running. This creates the cosmological horizon. There's a distance beyond which we can never see events happening now because light from those events will never reach us. Currently, this horizon is at about 16 billion light-years. Galaxies beyond this horizon are receding so fast that light leaving them today will never reach us, no matter how long we wait. As the universe continues to expand, this horizon will change. Observations show the expansion is accelerating, driven by dark energy. Dark energy is a mysterious component of the universe that causes the expansion to speed up over time. We don't know what dark energy is, but we can measure its effects. About 68% of the universe's total energy density is dark energy. About 27% is dark matter, and only about 5% is normal matter, the stuff we're made of. As dark energy drives the expansion to accelerate, distant galaxies will recede faster and faster. Eventually, even galaxies we can currently see will recede beyond the cosmological horizon and disappear from view. In the far future, trillions of years from now, only our local group of galaxies will remain visible. Everything else will have receded beyond the horizon. Future observers would see a nearly empty universe with only a few nearby galaxies visible and no sign of the wider cosmos. This is one of the sobering implications of the speed of light limit combined with cosmic expansion. The observable universe is shrinking in a sense, not because things are getting closer, but because the expansion is carrying distant regions beyond our ability to observe them. The speed of light, as fast as it is not fast enough to keep up with the expansion of space on cosmic scales. Let me bring everything together. The speed of light is 186,000 miles per second. This is the fastest speed possible in the universe. Nothing with mass can reach this speed, because doing so would require infinite energy. As you approach light speed, time slows down, distances contract, and mass increases. These effects are real, not illusions, and they've been confirmed by countless experiments. The speed of light creates a limit on how fast information can travel, which limits how quickly cause and effect can propagate. It shapes our ability to explore space, to communicate across cosmic distances, and to interact with the universe. It creates isolation on large scales, but connection across time. It allows us to see the history of the universe by looking at distant objects whose light has taken billions of years to reach us. The speed of light is not just about light, it's about the structure of space-time itself. It's the maximum rate at which you can move through space relative to time. It's built into the equations of relativity and quantum field theory. It's confirmed by observations ranging from GPS satellites to particle accelerators to cosmic rays to gravitational waves. And it's fundamentally connected to causality and the logical structure of the universe. Understanding the speed of light means understanding that reality is stranger than it appears. Time is not absolute. Distance is not fixed. Simultaneity is relative, and there's a cosmic speed limit that nothing can exceed. These ideas revolutionized physics in the 20th century. They changed how we think about space and time, and matter and energy. They enabled technologies like GPS and particle accelerators. They shaped our understanding of the cosmos, from the smallest particles to the largest scales of the universe. And they continue to inspire physicists today as we push the boundaries of knowledge. We've tested relativity in extreme conditions, near black holes and in the early universe, and it continues to work. We've searched for deviations from the speed of light limit and found none. Everything we observe is consistent with the speed of light being a fundamental constant that governs how the universe operates. As we look to the future, the speed of light will continue to shape what's possible. It will limit how fast we can travel to other star systems. It will determine how we communicate with future space colonies. It will affect how we explore and understand the cosmos. We may develop new technologies that allow us to approach the speed of light more closely than we can today. Matter-antimatter rockets, laser-pushed light sails, or propulsion methods we haven't imagined yet. But we'll never exceed the speed of light. We'll never break this fundamental barrier. Instead, we'll work within it, using time dilation to make long journeys feasible from the traveler's perspective, even if they take generations from Earth's perspective. We'll use the speed of light to probe the universe, sending signals and receiving information across vast distances. We'll continue to study light itself, the electromagnetic radiation that carries information from every corner of the cosmos. And we'll continue to refine our understanding of space-time, gravity, and the fundamental structure of reality. The speed of light is a window into the deepest laws of physics. It connects electromagnetism, relativity, quantum mechanics, and cosmology. It's a single number that appears throughout physics, a constant that shapes everything. And understanding it, really grasping what it means and why it exists, is essential to understanding the universe we live in. The speed of light breaks our everyday intuitions about space and time. It shows us that reality doesn't work the way we expect from daily experience. It reveals a universe where time is relative, where distances change with motion, where the future and past are defined by light cones, where causality has a maximum propagation speed. This is unsettling at first. It contradicts common sense. But it's true. Every experiment confirms it. Every observation supports it. The universe operates according to these strange rules, and the speed of light is at the center of it all. So, when you see starlight tonight, remember that you're seeing photons that traveled at the universe's ultimate speed. They crossed light years or millions of light years of space, taking years or millions of years to make the journey. They carry information from the past, from distant places, from stars and galaxies we can never reach, and they arrive at your eye at exactly 186,000 miles per second. The cosmic speed limit, the fundamental constant that shapes reality itself. This is the speed of light, the limit that breaks our reality and reveals the true nature of the universe. Thanks for joining me on this journey through physics and cosmology. The speed of light is one of the most important constants in all of science. It's a number that defines what's possible and what's not. It's a barrier that can't be crossed, and it's a key to understanding space, time, matter, and energy. Good night, and keep looking up at the stars, knowing that the light you see has traveled the cosmos at the speed that governs everything. Now let's think about what would happen if you could actually travel close to light speed. Imagine you're on a spacecraft accelerating continuously at 1 g, the same acceleration you feel standing on Earth's surface. This is comfortable for humans. You'd feel normal weight throughout the journey. If you accelerate at 1 g continuously, you'd reach 99% of light speed in about 2.5 years from your perspective. But here's where things get interesting. From Earth's perspective, you're experiencing time dilation. The faster you go, the slower your clock runs relative to Earth. If you accelerated at 1 g for what felt like 5 years to you, you'd be traveling at 99.99% of light speed. At that speed, time dilation is extreme for every year that passes for you. About 70 years pass on Earth. You could travel to the center of our galaxy, 26,000 light-years away, in what feels like about 20 years to you. But when you returned, over 52,000 years would have passed on Earth. Everyone you knew would be dead. Civilizations would have risen and fallen. The entire course of human history could have changed. You'd return to a world utterly different from the one you left. This is the twin paradox, made real and extreme. It's not really a paradox, just a consequence of special relativity, but it has profound implications for space travel. If we could build spacecraft capable of sustained acceleration to relativistic speeds, time dilation would actually make interstellar travel feasible from the traveler's perspective. You could visit distant star systems within a human lifetime, your lifetime, but you'd be traveling one way into the future. There's no going back to your own time. This creates fascinating scenarios for future civilizations. Imagine a network of human colonies scattered across the galaxy. Travel between them would be possible, but every journey would be a journey through time as well as space. Travelers would age slowly, while decades or centuries passed at their origin and destination. They'd become living time capsules, carrying information and culture from one era to another. This could actually be advantageous in some ways. A scientist could conduct research, travel to another star system taking decades from Earth's perspective, but only months from their own, and return with findings while still young enough to continue their career. Or a message could be hand-delivered across interstellar distances by a courier who experiences only a brief journey. But it would also create strange social dynamics. Families would be separated across time, not just space. Parents might watch their children age and die during a single round-trip journey. Relationships would be strained or impossible across these time gulfs. And anyone who frequently traveled between stars would become unstuck in time, never quite belonging to any single era. Science fiction has explored these ideas extensively, but they're based on real physics. If we develop the technology for relativistic space travel, these scenarios could become reality. Let me talk about simultaneity in more depth, because it's one of the strangest consequences of relativity. In everyday life, we think events either happen at the same time or they don't. Simultaneity seems absolute and universal, but special relativity shows this isn't true. Whether two events are simultaneous depends on your frame of reference. Here's a thought experiment. Imagine you're standing at the exact midpoint of a moving train. Lightning strikes both ends of the train simultaneously from your perspective. The light from both strikes reaches you at the same moment because you're equidistant from both ends. From your perspective on the train, the strikes were simultaneous, but someone standing on the platform sees something different. The train is moving, so by the time the light from the strikes reaches the platform observer, the train has moved. Light from the strike at the rear of the train has to travel farther to reach the platform observer than light from the front strike. From the platform observer's perspective, the front strike happened first, then the rear strike. Same events, different time ordering, depending on your motion. Who's right? Both are. There's no absolute sense in which the strikes were or weren't simultaneous. Simultaneity is relative. This seems impossible, but it's a direct consequence of the speed of light being constant for all observers. If light speed is the same for everyone, then different observers moving relative to each other must have different definitions of simultaneity. For events that could be causally connected, meaning one could influence the other, all observers agree on time ordering. If event A causes event B, every observer sees A before B. Causality is preserved. But for events separated by space, like distances that light couldn't cross in the time between them, different observers can disagree on which happened first. These are called space-like separated events. Their time ordering is ambiguous. This has been tested experimentally. Particle physics experiments routinely observe events at relativistic speeds, and the results always match relativity's predictions. Simultaneity is relative, causality is preserved, and the speed of light determines which is which. Let's talk about the energy required to accelerate to relativistic speeds. The kinetic energy of an object is 1/2 mass times velocity squared in classical physics. This works fine at everyday speeds, but it breaks down as you approach light speed. In relativity, the kinetic energy formula is different. It's mass times the speed of light squared times a factor that depends on velocity at low speeds. This reduces to the classical formula. But as you approach light speed, the energy required grows without limit. To accelerate 1 kilogram of mass to 90% of light speed requires about 11 million billion joules of energy. That's about the energy in 270 million kilograms of TNT. To reach 99% of light speed requires about 44 million billion joules. To reach 99.9% requires about 158 million billion joules. The energy grows exponentially as you get closer to light speed, and to actually reach light speed would require infinite energy. This is why you can't reach light speed. It's not just difficult, it's literally impossible. You'd need infinite energy, which doesn't exist. For comparison, the total energy output of the Sun is about 384 million trillion joules per second. To accelerate 1 kilogram to 99.9% of light speed would require the Sun's total output for about 7 minutes. To accelerate a spacecraft with a mass of 10,000 kilograms, about the mass of the Hubble Space Telescope, to 99.9% of light speed would require the Sun's total output for about 4 months. And that's just to accelerate it. To slow down at your destination requires the same amount of energy again. These numbers are staggering. They show why interstellar travel at relativistic speeds remains far beyond our current capabilities. We'd need energy sources and propulsion systems far more efficient than anything we have today. Matter-antimatter annihilation is theoretically the most efficient possible, converting 100% of mass to energy. But even with perfect efficiency, you'd need huge amounts of fuel. To accelerate a spacecraft to a significant fraction of light speed using matter-antimatter propulsion would require fuel masses comparable to the spacecraft's own mass. And we don't know how to produce, store, or control antimatter in the quantities needed. These are fundamental engineering challenges, not just technological ones. We're not talking about building better rockets with existing technology. We're talking about harnessing energy and matter in ways we've never done before. Let's discuss some more consequences of the speed of light for how we understand the universe. The finite speed of light means we can see the history of the universe by looking at different distances, This has allowed us to piece together the entire history of cosmic evolution. We see nearby galaxies as they were relatively recently, millions of years ago. We see more distant galaxies as they were billions of years ago. And we see the cosmic microwave background as it was just 380,000 years after the Big Bang. By combining observations at different distances, we can trace how galaxies evolved over cosmic time. We can see how galaxies were different in the early universe, smaller and more irregular, and how they grew and changed over billions of years to become the mature spiral and elliptical galaxies we see nearby today. This is like archaeology, but instead of digging down through layers of Earth to find older artifacts, we look farther out into space to see older objects. The farther we look, the farther back in time we see. This has revealed that the universe has a history, that it has evolved and changed over time. Galaxies weren't always as they are now. Stars weren't always forming at the same rate. The universe itself was different in the past, denser, hotter, and more uniform. All of this we know because light travels at finite speed. If light traveled instantaneously, we'd see everything as it is now, and we'd have no way to observe cosmic history. The finite speed of light also affects how we think about the universe's expansion. When we measure how fast distant galaxies are receding, we're measuring their speed when the light left them, not their speed now. For very distant galaxies, this was billions of years ago. The universe has continued expanding since then, so those galaxies are even farther away now and receding even faster. This complicates cosmological measurements. We have to account for how the expansion rate has changed over cosmic history. Early in the universe, the expansion was decelerating due to the gravitational pull of all the matter. But about 6 billion years ago, dark energy started dominating, and the expansion began accelerating. By observing supernovae at different distances, which tells us about different cosmic epochs, astronomers discovered this accelerating expansion. This discovery won the Nobel Prize in Physics in 2011. It was completely unexpected and has profound implications. The accelerating expansion means the universe's fate is different than we thought. Instead of eventually recollapsing in a big crunch or expanding forever but gradually slowing down, the universe will expand faster and faster without limit. Eventually, distant galaxies will be receding so fast that we'll lose sight of them forever. They'll cross beyond the cosmic horizon. And all of this we discovered by measuring light that traveled for billions of years at the speed of light. Let's talk about light's relationship to particle physics. In the standard model of particle physics, particles are classified partly by their mass. Particles with mass always travel slower than light. Particles without mass always travel at exactly light speed. Photons, the particles of light, have zero mass. This is why they travel at light speed. It's not just that they happen to travel at this speed, they must travel at this speed because they're massless. Gluons, which carry the strong nuclear force, are also massless and travel at light speed. If gravitons exist, the hypothetical particles that carry gravity, they'd be massless and travel at light speed too. Massive particles like electrons, quarks, and the W and Z bosons that carry the weak nuclear force all travel slower than light. Neutrinos were once thought to be massless, but experiments in the 1990s and 2000s proved they have a tiny mass. This means they travel very close to light speed, but not quite at it. The discovery that neutrinos have mass was a major finding because it means the standard model is incomplete. The standard model as originally formulated had massless neutrinos. The fact that they have mass means we need to extend the model. This is still an active area of research. We know neutrinos have mass, but we don't know exactly how much mass or what mechanism gives them mass. It's probably different from the Higgs mechanism that gives mass to other particles. Understanding neutrino masses is one of the open questions in particle physics, and it all connects back to the speed of light. Massless particles travel at light speed, massive particles don't. By measuring whether a particle travels at light speed or not, we can determine whether it has mass. This has been used in experiments to set upper limits on photon mass. If photons had even a tiny mass, they'd travel slightly slower than light speed, and we could detect this by looking at light from very distant sources. Light of different energies would arrive at slightly different times if photons had mass. We don't see this effect, which tells us photons are massless to extremely high precision. The same technique has been used to set limits on graviton mass. Gravitational waves travel at the speed of light to within our measurement precision. This tells us gravitons, if they exist, are massless or very nearly so. These measurements connect fundamental physics to the speed of light in profound ways. Now let's think about the speed of light from a more philosophical perspective. Why does the universe have a speed limit at all? Why is light speed finite rather than infinite? These are deep questions that touch on the nature of space and time. One way to think about it is that the speed of light is the speed of causality. It's the fastest speed at which cause and effect can propagate. If this speed were infinite, if information could travel instantaneously across any distance, the universe would be very different. There'd be no time delays, no light travel times, no looking back in time when we look far into space. Causality would be instant and universal, but this would create problems. If effects could propagate instantaneously, you could have causal loops and paradoxes. You could affect your own past, creating grandfather paradoxes. The universe would be logically inconsistent. The finite speed of light prevents this. It creates a structure in space-time where causality flows in consistent directions. Your future light cone contains all events you can possibly affect. Your past light cone contains all events that can possibly have affected you. Events outside your light cone are causally disconnected from you. This structure ensures logical consistency. You can't affect your own past because your past is in your past light cone, and you can only affect events in your future light cone. These don't overlap. So the finite speed of light isn't just a random feature of the universe. It's necessary for the universe to make logical sense. It's what allows time to have a direction, what allows cause to precede effect, what makes physics predictable and consistent. In a deep sense, the speed of light is one of the fundamental constants that determines the structure of reality itself. Along with things like the strength of gravity, the charge of the electron, and the mass of the Higgs boson, the speed of light is a parameter that defines what kind of universe we live in. Change the speed of light, and you'd change everything. Make it slower, and causality would be even more constrained. The universe would feel smaller, light would take longer to cross distances. Make it faster, and causality would be less constrained. The universe would feel larger. We could communicate and travel across larger distances more easily. Make it infinite, and you'd break causality entirely, creating a logically inconsistent universe. The speed we have, 186,000 miles per second, is what we've got, and it shapes everything about reality. Let me talk about one more application of the speed of light: GPS. Your smartphone can pinpoint your location to within a few yards using signals from satellites orbiting Earth. This seems simple, but it requires accounting for both special and general relativity. GPS satellites orbit at about 12,550 miles above Earth's surface. At this altitude, they're moving at about 8,600 miles per hour relative to the ground. Because they're moving, special relativity predicts their clocks should run slow by about 7 microseconds per day compared to clocks on the ground. But they're also in a weaker gravitational field than clocks on the ground. General relativity predicts that clocks in weaker gravity run faster. At the satellite's altitude, this effect causes clocks to run fast by about 45 microseconds per day. The two effects partially cancel, but the net result is that satellite clocks run about 38 microseconds per day faster than ground clocks. This might not sound like much, but GPS works by measuring how long it takes light-speed signals to travel from satellites to your receiver. Light travels about 984 feet in 1 microsecond. If the satellite clocks were off by 38 microseconds, your position would be wrong by about 7¼ miles after just 1 day. GPS corrects for this by adjusting the satellite clock rates. Before launch, the satellites are programmed to tick at a slightly different rate than ground clocks. Once in orbit, relativistic effects cause them to tick at the correct rate. Without these relativity corrections, GPS would accumulate errors of several miles per day. Within weeks, it would be useless for navigation. Every time you use GPS, you're relying on Einstein's theories of relativity. You're relying on the fact that time is not absolute, that it depends on motion and gravity. You're relying on the finite speed of light and how accurately we can measure it. GPS is a practical, everyday application of relativity. It's technology that wouldn't work without our understanding of how the speed of light and space-time work. This connection between fundamental physics and practical technology shows how understanding the universe at the deepest level can lead to tools that change daily life. As we come to the end of this journey, let's reflect on what the speed of light really means. It's 186,000 miles per second, a number we can write down, a speed we can measure. But it's so much more than just a number. It's the cosmic speed limit, the fastest anything can travel. It's the speed at which causality propagates, determining how quickly causes can produce effects. It's the conversion factor between space and time in the geometry of space-time. It's what allows us to look back in time by looking far into space. It's what creates cosmic horizons beyond which we can never see. It's what makes GPS work and allows us to navigate the world. It's what tells us about the mass or masslessness of fundamental particles. It's woven into the deepest structure of physical law, appearing in equations from Maxwell's electromagnetism to Einstein's relativity to quantum field theory. Understanding the speed of light means understanding that the universe is stranger and more wonderful than everyday experience suggests. Time is not a universal river that flows the same for everyone. Space is not an unchanging stage where events occur. They're interwoven into space-time, a four-dimensional fabric that bends and warps, where time can slow down and distances can contract, where the rules are determined by how fast you're moving and how strong gravity is. This understanding has transformed physics, enabled new technologies, and changed how we see our place in the cosmos. We're living in an era where we can detect gravitational waves from black holes billions of light years away, where we can use atomic clocks to test relativity to extraordinary precision, where we can accelerate particles to 99.999999% of light speed and watch them behave exactly as relativity predicts. Every experiment confirms what Einstein realized over a century ago. The speed of light is constant, and this simple fact requires us to reimagine space and time completely. As we look to the future, the speed of light will continue to shape what's possible. It limits how fast we can explore the cosmos, but it also enables us to see cosmic history. It constrains how we can communicate across the universe, but it also ensures logical consistency. It sets the ultimate speed limit, but it also reveals the deep structure of reality. The speed of light is not a limitation to be overcome. It's a fundamental feature of the universe, as basic as the 3 dimensions of space or the forward flow of time. It's part of what makes the universe comprehensible, predictable, and beautiful. So when you see starlight tonight, remember, You're seeing photons that have traveled for years or centuries or millennia at 186,000 miles per second. You're connected to distant stars and galaxies by light that bridges the cosmic void. You're seeing the universe not as it is, but as it was, looking back through time with every glance at the night sky. And you're witnessing the fundamental speed limit of reality itself, the cosmic constant that governs everything from the smallest particles to the largest structures in the universe. This is the speed of light, the limit that breaks our reality and reveals the true nature of the cosmos. Thank you for staying with me through this exploration of one of physics' most important constants. The speed of light shapes everything about how the universe works, from the behavior of subatomic particles to the expansion of space itself. It's a number that appears everywhere in physics, a constant that ties together seemingly unrelated phenomena, and it's a speed that we can measure, test, and use, even though we can never reach it. Understanding the speed of light means understanding the universe at its most fundamental level. It means grasping that reality is weirder and more wonderful than we ever imagined. It means accepting that time and space are not what they seem, that the rules change when you move fast or encounter strong gravity, and that the universe has a structure determined by light itself. Good night, and may you never look at light the same way again. Let me tell you about one of the most famous experiments that confirmed the constancy of the speed of light. In 1887, Albert Michelson and Edward Morley conducted an experiment that would change physics forever. At the time, physicists believed light traveled through a medium called the luminiferous ether. This was an invisible substance that supposedly filled all of space. Waves need a medium to travel through. Sound travels through air. Water waves travel through water. So physicists reasoned that light waves must travel through something. They called this hypothetical medium the ether. If the ether existed, Earth must be moving through it as we orbit the sun. This means we should detect an ether wind, like how you feel wind when you drive even on a calm day. Michelson and Morley designed an ingenious experiment to detect this ether wind. They built an interferometer, a device that splits a light beam in two, sends the beams in perpendicular directions, bounces them off mirrors, and recombines them. If Earth is moving through the ether, light traveling in the direction of Earth's motion should be affected differently than light traveling perpendicular to it. This would create an interference pattern that would shift as you rotated the apparatus. They performed the experiment with extraordinary precision, and they found nothing. No ether wind. No difference in light speed depending on direction. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. This was shocking. It contradicted everything physicists expected. Michelson and Morley repeated the experiment many times, at different times of day, different seasons, different orientations. Always the same result. Light speed is constant. This result baffled physicists for nearly 2 decades. Various explanations were proposed, including the idea that the ether was dragged along with Earth, or that objects contract in the direction of motion through the ether. But none of these explanations were fully satisfactory. Then Einstein came along with special relativity. He started with the experimental result that light speed is constant and worked out the consequences. Time must be relative, space must contract, simultaneity must depend on motion. These consequences seemed impossible, but they explained the Michelson-Morley result perfectly. And they made predictions that could be tested. One prediction was time dilation, which was confirmed by observing particle decays at high speeds. Another was length contraction, confirmed by measuring the sizes of fast-moving particles. Another was that energy and mass are equivalent, confirmed by nuclear reactions. Every prediction of special relativity has been confirmed by experiments. The theory works. And it all started from one experimental fact. Light speed is constant. Now let's talk about black holes again, but in more detail about what happens to light near them. Black holes are regions where gravity is so strong that not even light can escape. This happens when mass is compressed into a small enough volume. For a non-rotating black hole, there's a boundary called the event horizon. Inside the event horizon, all paths lead inward toward the singularity. Outside the event horizon, you can escape if you're moving fast enough. At the event horizon itself, you'd need to travel at light speed outward just to stay in place. Since nothing can travel faster than light, and you'd need to exceed light speed to escape from inside the horizon, escape is impossible. Light can orbit a black hole at a distance called the photon sphere. This is about 1.5 times the event horizon radius. At this distance, light can travel in circular orbits around the black hole. If you were at the photon sphere and looked in the right direction, you'd see the back of your own head because light from you would orbit the black hole and return. Closer than the photon sphere, light spirals inward, even if it's traveling tangentially. Farther than the photon sphere, light can escape, though its path is bent by the black hole's gravity. This bending of light by gravity is called gravitational lensing. We use it to study black holes, to map dark matter in galaxy clusters, and even to discover exoplanets. When light from a distant star passes near a massive object, the object's gravity bends the light path. This can create multiple images of the star, or magnify the star's light, or create arcs and rings. Einstein predicted this in 1915, and it was first observed during a solar eclipse in 1919. Stars near the Sun appeared slightly displaced from their normal positions because the Sun's gravity bent their light. This observation made Einstein famous worldwide. Today, we observe gravitational lensing all the time. The Hubble Space Telescope has captured beautiful images of Einstein rings, where a distant galaxy's light is bent around a foreground galaxy cluster, creating a ring or arc of light. These observations tell us about the mass distribution of the lensing object, including dark matter, which we can't see directly, but which reveals itself through its gravitational effects. They also allow us to study very distant galaxies that would be too faint to see without the magnification provided by lensing. Gravitational lensing is now a major tool in cosmology. It helps us map dark matter, study galaxy formation, measure distances across the universe, and test general relativity in strong gravitational fields. And it all depends on understanding how light travels through curved space-time. Let me talk about the cosmological constant and dark energy in relation to the expansion of space and light. When Einstein developed general relativity, he added a term to his equations called the cosmological constant. This was a form of energy inherent to space itself. Einstein added it because he believed the universe was static, neither expanding nor contracting. Without the cosmological constant, his equations predicted the universe should be either expanding or contracting. Gravity pulls everything together, so a static universe should collapse. The cosmological constant provided a repulsive force to balance gravity and keep the universe static. But then Hubble discovered that the universe is expanding. Galaxies are moving apart, and the farther away they are, the faster they're receding. Einstein reportedly called the cosmological constant his greatest blunder. If he'd trusted his equations without adding the constant, he could have predicted the expanding universe before it was observed. For decades after this, most physicists assumed the cosmological constant was zero. The universe was expanding, and gravity was gradually slowing the expansion. Eventually, the expansion might slow enough to reverse, leading to a big crunch, or it might continue forever, with the expansion gradually approaching zero speed. But observations of distant supernovae in the late 1990s shocked everyone. The expansion isn't slowing down. It's speeding up. Distant galaxies are receding faster than they should be if gravity were the only force acting. Something is pushing space apart, causing the expansion to accelerate. Physicists call this dark energy, and it behaves very much like Einstein's cosmological constant. It's energy inherent to space itself. As the universe expands and more space is created, there's more dark energy. This causes the expansion to accelerate. About 68% of the universe's total energy density is dark energy. It dominates over matter, both normal and dark, and it's causing the universe to expand faster and faster. This has profound implications for the future. As dark energy drives accelerating expansion, distant galaxies will eventually recede faster than light, not because they're moving through space faster than light, but because space itself is expanding faster than light can cross it. These galaxies will cross beyond our cosmic horizon and disappear from view. Given enough time, in the far future, only our local group of gravitationally bound galaxies will remain visible. Everything else will have receded beyond the horizon. Future astronomers wouldn't be able to see the distant universe. They wouldn't be able to observe the cosmic microwave background. They might not know the universe had a Big Bang or that it's expanding. They'd see an apparently static universe containing only their local group. We're fortunate to live in an era when we can still see the wider cosmos. The speed of light, combined with cosmic expansion and dark energy, has created a limited window in cosmic history when the universe is comprehensible. Before this era, the universe was too young and small for complex structures to have formed. After this era, the accelerating expansion will hide most of the universe from view. We happen to exist during the window when intelligent beings can observe and understand the cosmos. This might not be coincidence. Perhaps the conditions that allow for life and intelligence are the same conditions that allow for cosmic visibility. This is speculation, but it's fascinating to think about. Let's return to the practical question of space exploration and what the speed of light means for humanity's future among the stars. With current technology, we're limited to exploring our own solar system. We've sent probes to all the planets, and some have left the solar system entirely. Voyager 1 is now in interstellar space, over 14 billion miles from Earth. It's been traveling for over 45 years and is moving at about 38,000 miles per hour. At this speed, it would take about 70,000 years to reach the nearest star if it were headed in that direction, which it's not. Pioneer 10 and 11, launched in the 1970s, are also in interstellar space, heading in different directions. They carry plaques with information about Earth and humanity, messages in a bottle for any alien civilization that might find them billions of years from now. But these spacecraft are not designed for interstellar travel. They're moving slowly, they have no navigation systems capable of targeting other stars, and their power sources will die long before they reach anywhere interesting. They'll drift through interstellar space, essentially forever, silent and dark. To actually explore other star systems, we need to go much faster, at least a few percent of light speed, preferably 10 or 20%. This requires new propulsion technologies. Nuclear pulse propulsion could potentially reach a few percent of light speed, but it requires detonating thousands of nuclear bombs and hasn't been tested. Fusion propulsion, if we can ever make fusion work reliably, could reach similar speeds. Matter-antimatter propulsion could theoretically reach much higher speeds, but we can't produce or store antimatter. Laser-pushed light sails like Breakthrough Starshot might reach 20% of light speed, but only for very small probes. Each of these technologies faces enormous challenges, but they're based on known physics. They're difficult, not impossible. If humanity commits resources to developing these technologies over the coming decades or centuries, interstellar exploration could become reality. Probes could be sent to Alpha Centauri, arriving after 20 or 30 years of flight time. They'd send back data about any planets there, whether they're habitable, whether they harbor life. This data would take another 4.37 years to reach Earth at light speed. So we'd be looking at a total mission time of around 30 to 40 years from launch to receiving the first data. That's within a human lifetime. The people who designed and launched the mission could still be alive to see the results. This makes near-term interstellar exploration at least conceivable, if technically very challenging. Crewed missions are another matter entirely. Sending humans to other stars requires life support for years or decades, shielding from radiation, some way to slow down at the destination, and a way to return, assuming you want to return. Multi-generational ships, where the people who arrive are descendants of those who launched, are often proposed, but these would need to be entirely self-sufficient ecosystems lasting for centuries. We've never built anything close to this. Suspended animation, or some form of stasis, might make it feasible within a single generation. But we don't have this technology and don't know if it's even possible. Using time dilation by traveling at very high speeds is another option. If you could accelerate to 99.9% of light speed, you could reach Alpha Centauri in a few weeks of ship time. But you'd need enormous amounts of energy, and when you returned, decades would have passed on Earth. All of these scenarios are limited by the speed of light. No matter how advanced our technology becomes, we can't exceed this limit. We can approach it more and more closely, but we can never reach it. This means interstellar exploration will always be slow by human standards, taking years or decades or longer. It requires patience, long-term thinking, and a willingness to invest in projects whose results won't be seen for generations. These are things human civilization has struggled with. We tend to think in terms of years or decades, not centuries. But if we want to explore the stars, we need to think on these longer timescales. The speed of light isn't just a physical limit, it's a psychological and cultural challenge. It forces us to think beyond our own lifetimes, to care about outcomes we won't live to see. In a sense, it's a test of whether we can transcend our short-term nature and become a truly long-term civilization. As we approach the end of this journey, I want to emphasize how extraordinary it is that we understand the speed of light at all. For most of human history, we didn't even know light had a speed. It seemed instantaneous, too fast to measure. Only 400 years ago did we first prove light speed is finite. Only 150 years ago did we measure it accurately. And only just over a century ago did we understand what it really means, that it's not just a speed, but a fundamental feature of space-time itself. This understanding required brilliant insights from physicists across generations. Maxwell figuring out that light is electromagnetic waves, Michelson and Morley proving light speed is constant, Einstein reimagining space and time to make sense of that constancy, and countless others who tested, refined, and extended these ideas. Today we can measure the speed of light to extraordinary precision. We define our units based on it. We use it in technologies like GPS that billions of people rely on every day. We test relativity's predictions in particle accelerators and astronomical observations, and every test confirms what Einstein told us. Light speed is constant, time is relative, and space and time are interwoven. This is one of humanity's greatest intellectual achievements. We've uncovered a fundamental truth about reality that wasn't obvious, that contradicted common sense, but that turned out to be correct. And we did it through observation, experimentation, and mathematical reasoning. This is science at its best. Taking something that seems simple, why does light travel at the speed it does, and digging deeper until you find profound truths about the structure of the universe. The speed of light connects to everything in physics. It's in Maxwell's equations of electromagnetism. It's in Einstein's equation E equals mc squared. It's in the theories of quantum fields and particles. It's in cosmological models of the universe's expansion. It appears everywhere because it's fundamental to how reality works. Understanding it means understanding the universe at its deepest level, and that understanding continues to grow. We're still discovering new implications of relativity, still testing it in new regimes, still using it to probe the frontiers of physics. The speed of light is not just a historical discovery, it's a living part of modern science. It guides our exploration of black holes and gravitational waves. It shapes our models of the early universe. It constrains our theories of quantum gravity. Every new discovery in physics connects back to this fundamental constant. 186,000 miles per second, the cosmic speed limit. The speed at which light travels, at which causality propagates, at which the universe reveals itself. This is the speed that governs everything, and understanding it means understanding reality itself. Thank you for joining me on this deep exploration of the speed of light. It's been a journey through physics, history, and the fundamental nature of space and time. The speed of light is one of the most important constants in all of science, and I hope you now understand why. It's not just a number, it's a window into how the universe works at its most basic level. Good night, and remember, every time you see light, you're witnessing the cosmic speed limit in action. Let's explore one more fascinating implication of the speed of light, the information paradox at black hole event horizons. When something falls into a black hole, what happens to the information it carries? According to classical general relativity, it disappears behind the event horizon and is lost forever. But quantum mechanics says information can't be destroyed. This creates a paradox. Stephen Hawking worked on this problem for decades. He showed that black holes emit radiation due to quantum effects near the event horizon. This is called Hawking radiation. Over extremely long timescales, black holes can evaporate completely through this radiation. But Hawking radiation is thermal, meaning it's random and doesn't carry information about what fell in. So, the information that fell into the black hole would be lost when the black hole evaporates. This violated a fundamental principle of quantum mechanics. Hawking initially argued that information must be destroyed, that this was one place where quantum mechanics broke down. But most physicists disagreed. The debate raged for years. It's now believed that information is somehow encoded in the Hawking radiation in subtle ways we don't fully understand. The holographic principle suggests that all the information about what's inside a black hole is encoded on its event horizon, like a hologram, and this information gets released as the black hole evaporates, though we don't know exactly how. This connects to the speed of light because the event horizon is defined by light. It's the surface where light traveling outward stays in place. Inside this surface, even light gets pulled inward. Outside, light can escape. The boundary between these regions is determined entirely by light's behavior. And the information paradox involves understanding what happens to information at this light-defined boundary. Solving this paradox completely will probably require a theory of quantum gravity, combining quantum mechanics with general relativity. We don't have such a theory yet, but physicists are working on candidates like string theory and loop quantum gravity, and the speed of light will undoubtedly play a central role in whatever theory turns out to be correct. Let me also tell you about tachyons, hypothetical particles that travel faster than light. In special relativity, the equations allow for particles with imaginary mass. These particles would always travel faster than light. They're called tachyons. If tachyons existed, they'd have very strange properties. They'd go faster when they lose energy, and slower when they gain energy. They'd travel backward in time from some reference frames. They'd create causality violations. Most physicists think tachyons don't exist. There's no experimental evidence for them, and their existence would create serious problems with causality and the logical consistency of physics. Whenever theoretical models predict tachyons, it's usually a sign that the model is unstable or wrong. The tachyon appears as a mathematical artifact, not as a real particle. So while tachyons are mathematically possible in relativity, they're not thought to be physically real. The speed of light remains the absolute speed limit. Nothing goes faster. This brings us back to a fundamental question. Could the laws of physics be different? Could there be universes where the speed of light is different? This is speculative, but it's an interesting thought experiment. If the speed of light were slower, say 100,000 miles per second instead of 186,000, what would change? Causality would still work, but it would be more constrained. Light would take longer to travel the same distances. The universe would feel smaller in a sense. But the fundamental structure of relativity would be the same. If the speed of light were faster, the universe would feel larger. Causality would be less constrained, but again, the basic physics would work similarly. If the speed of light were infinite, that's where things break down. Causality would fail, paradoxes would arise, and the universe wouldn't be logically consistent. So there seems to be something special about light speed being finite but not zero. It needs to be large enough that the universe is interesting, small enough that causality is preserved. The actual value, 186,000 miles per second, might be arbitrary. But the fact that it's finite and not infinite seems necessary for the universe to make sense. Now, let me talk about quantum entanglement one more time, because it often confuses people in relation to the speed of light. When two particles are entangled, measuring one instantly affects the other, even if they're light years apart. This seems to violate the speed of light limit. If the effect is instantaneous, isn't information traveling faster than light? The answer is subtle but important. No information travels faster than light. Here's why. When you measure an entangled particle, you get a random result. You can't control what result you get. The other particle gets the opposite result, instantly. But the person at the other particle doesn't know you measured yours. They just see random results. Only when they compare results with you, using normal communication that travels at light speed or slower, do they discover the correlation. So the correlation is instantaneous, but discovering the correlation requires classical communication at light speed or slower. No information travels faster than light. You can't use entanglement to send a message. You can't signal. This is sometimes called the no communication theorem in quantum mechanics. Entanglement is real. It's been confirmed by countless experiments, but it doesn't violate relativity. The two theories are compatible. This was a huge relief to physicists who spent decades worrying about whether quantum mechanics and relativity could coexist. They can, and they do. The speed of light limit is preserved even in the quantum realm. Let me close with some thoughts on what all of this means for our place in the universe. The speed of light creates isolation. We're separated from the rest of the cosmos by vast distances that light takes years or millions or billions of years to cross. We can see distant galaxies, but we can never touch them, never visit them, never communicate with them in real time. We're confined to our local neighborhood of space. Even traveling at light speed, which is impossible, we couldn't explore even a tiny fraction of the universe in a human lifetime. This is humbling. It reminds us how small we are, how isolated, how limited in our reach. But it's also liberating in a way. The speed of light forces us to focus on what's near, what's achievable, what's within our local realm. It encourages us to appreciate the one planet we have, the one solar system we can actually explore. It makes the cosmos more precious because it's largely out of reach. We can observe and study and wonder, but we can't conquer or control. The universe remains wild and vast and mysterious, and perhaps that's how it should be. The speed of light also connects us across time. Every photon that enters our eyes has traveled from the past. Starlight is ancient, carrying information from distant times and places. When we look up at the night sky, we're not seeing the universe as it is now. We're seeing a collage of different times. Near stars from the recent past, distant galaxies from the ancient past, all mixed together in our view. This is profound. It means we're connected to cosmic history through light. We're witnesses to events that happened long ago and far away. We're participants in a universe that has a deep and complex history stretching back to the Big Bang. Understanding the speed of light helps us understand our place in this history. We're latecomers, living in a universe that's 13.8 billion years old. We've existed for only a tiny fraction of cosmic time, but we're here now, able to observe and understand, and that's extraordinary. The speed of light is the thread that connects us to everything else in the cosmos. It's how information reaches us from distant stars and galaxies. It's how we learn about black holes and supernovae and the expanding universe. It's the carrier of knowledge across the cosmic void, and it's 186,000 miles per second. Not instantaneous, but fast enough to span the cosmos. Not infinite, but finite enough to preserve causality and make the universe comprehensible. This is the speed of light, the limit that shapes reality, the constant that appears in every corner of physics, the speed at which the universe reveals itself to us. Understanding it means understanding our place in space and time. It means grasping that we live in a relativistic universe where the rules are strange and beautiful. It means accepting that some things are beyond our reach, but celebrating what we can observe and discover. Thank you for joining me on this journey into the nature of light, speed, and space-time. The speed of light is more than just a number. It's a fundamental truth about reality, and now you understand why. Good night, and may the light from distant stars remind you of the cosmic speed limit that governs all of existence. Let me share one final perspective on the speed of light that brings everything together. Imagine you could somehow stand outside the universe and watch it unfold. You'd see light traveling at its finite speed, connecting distant events, carrying information across space. You'd see how this finite speed creates structure in space-time, how it defines causality and prevents paradoxes, how it allows time to have meaning and direction. The speed of light isn't arbitrary. It's woven into the deepest fabric of reality. Change it, and you'd change everything about how the universe works. Make it infinite, and causality breaks down entirely. Make it too slow, and the universe becomes too constrained, too limited. The value we have, 186,000 miles per second, allows for a universe that's vast yet comprehensible, connected yet causal, mysterious yet knowable. It's a universe where light can travel across cosmic distances, where we can see billions of light years into space and time, but where we're also limited and humbled by those same vast scales. This balance is what makes our universe interesting. It's what allows for complexity, for structure, for life and intelligence to emerge. In a universe with instantaneous communication, there'd be no time for things to evolve separately, no isolation to allow for diversity. In a universe with a much slower speed limit, there'd be no way to see distant objects, no way to piece together cosmic history. We have just the right speed limit to allow for a rich, complex, comprehensible universe. And we're fortunate to live in an era when we can understand this. When we have the technology to measure light speed precisely, to test relativity's predictions, to observe the cosmic consequences of this fundamental limit. Our ancestors couldn't know any of this. They saw the same stars, but they didn't understand the vast distances or the travel time of light. They couldn't know that looking at stars means looking into the past. Future beings, if they exist trillions of years from now, might not be able to discover what we've learned. The accelerating expansion might hide so much of the universe that future astronomers couldn't piece together the full story. We're in a special time, a cosmic sweet spot where the universe is old enough to be interesting, but young enough to be observable. The speed of light made this possible. It preserved information from the distant past, allowing us to see the cosmic microwave background and ancient galaxies. It created structure and complexity through the interplay of finite light speed and cosmic expansion. It gave us a universe worth exploring and understanding. So when you think about the speed of light, don't just think of it as a speed limit. Think of it as the fundamental constant that makes our universe what it is. The number that appears in equations across all of physics. The speed at which reality propagates. The cosmic thread connecting everything from the smallest particles to the largest scales. 186,000 miles per second. It's not just fast, it's perfect. It's exactly what it needs to be for this universe to exist as it does. And understanding it means understanding something profound about the nature of existence itself. Thank you for exploring this with me. The speed of light is one of the great constants of physics, and now you know not just what it is, but why it matters. It shapes everything about how the universe works, from the behavior of individual photons to the evolution of the entire cosmos. It's a speed limit we can never break, a boundary we can never cross. But it's also a window into the deepest truths about space, time, and reality. Every time light enters your eyes, remember that you're experiencing this fundamental constant in action. You're connected to the cosmos at the speed of light, and that connection reveals the true nature of the universe we inhabit. Good night, and may you forever see light differently, knowing now what it truly represents.